Okay, so this is my recording for AI assignment 1. I'm running my solution in the command prompt through Python. Let's run easy problem with breadth first search, outputs everything. Medium problem with A star, again outputs the whole solution, and hard problem with greedy best first search. Takes a couple seconds and then outputs the whole thing. This is outputting the full all whatever 52 steps that are there. And then it just lets you cycle around and it'll let you input a new problem if you want to. So I'm modeling the 8 problem with my states are a 2D array of the numerals, and my successor functions go through. I track where the blank is. I track the row and the column of where the current blank is. And then these successor functions are just down, up, left, right, and then I know what action was taken to get to that state. And so I'm just swapping around what was in the blank and like what the next thing is, and checking to make sure I'm not at an edge. And these 4 functions are very similar in that they're just swapping the one and always checking if they're on the edge. And that's used in my node class. It will, if you call successor on a node, it returns a list of all the successors to the current data that it has. So it'll call up, down, left, right, and then it saves the action that was used to get there. And the hash of the board state is based off of those numerals. So I have a search class that is a superclass, and it actually won't work. It basically has a pure virtual function that's called and isn't defined in this class, but it's only defined in these subclasses. So you initialize it, and you pass in the initial state that you're starting from, and then the goal state is always constant. And then you'll call find solution. That starts up the node list. And the node list, I'm using a deck to do that because I wanted to push and pop off of both ends, and that seemed like it was easiest to do in Python with that. And then I have a set for checking for duplicates, so then I can easily it just hashes the board state, checks if that's in there, and within a constant time it tells whether I've visited that yet. And so this is my whole all the searches do this while true, pop off the node. If you're at the goal, save the solution, and so we can print it later. If you're not at the goal, get all the successors, and then use add node to list on that successor node. So add node to list checks have we visited this before by checking whether it's in the set. If we haven't visited it before, polymorphically add it to the queue, so that's those are the different searches, do that different ways. Add it to the sets and track some other numbers. Save solution is just what's called at the end to save off all the data, and then print solution prints it all pretty nicely. So the different subclasses. Let's look at simpler ones. Look at breadth first, search first. So this is called within add node to list. This is just still like the very low level. How does it get added to the list? Breadth first search appends it to the end. Depth first search pushes it onto the front. More complicated, we'll get A star. A star appends it to the end, and then I'm turning that list of nodes into a Python list and then sorting it by the result of F. And that F is called on every node, and then it's resorted. And so that's how they keep in order. Greedy best search, I'm doing a slightly more complicated. It's actually it's trying to insert it in the correct spot without resorting the entire list. And these two, if you look, they're really different. These two implementations are really different, and I tried both ways on both things, and this is just what ended up running faster for each of them, and I'm not quite sure why. It might just be the given test cases. They might just be special cases. I think that's everything. Oh, and my UI is down here at the bottom. Oh, and then these heuristic functions are over here in global namespace. And the UI is pretty simple.